안녕하세요. 오늘은 사이클로알케인과 그리고 스테레오케미스트리에 관한 것을 알아보도록 하겠습니다. Why do we learn this chapter? Because cyclic compounds are a major class of biomolecules, such as proteins, lipids, carbohydrates, and nucleic acids. You can find the cyclic structures in the side chain of the amino acid. Also, seldom you find the cyclic structure of the fatty acid derivatives. Also, most of monosaccharides exist as a cyclic compounds, 5-membered ring or 6-membered ring. And the basis of nucleic acids are also cyclic compounds. It's very important to understand the properties of cyclic compounds because those cyclic compounds plays a very important role in the biomolecules. We'll start this chapter with the nomenclature of cyclic compounds. Okay. The general formula for the cyclic compound can be represented as CnH2n. Remember that the general formula for the alkane with the single double bond is also expressed as CnH2n, okay? The simplest cyclic structure is cyclopropane. It is CH2, CH2, and CH2. We can consider 4-membered ring, that is cyclobutane, 5-membered ring, cyclopentane, and cyclohexane. We are going to learn the structural properties of these cyclic compounds and their relationship to the energies. Let's try to learn the nomenclature of cyclic compounds, just like the nomenclature of alkanes. The first step for the nomenclature of a cycloalkane is to find the parent carbon in the ring. If the molecules contains cycles and linear chains, then compare the number of carbons in the cycle with the number of carbons in the linear chain and pick up the one which has the higher number of carbons as a parent. The second step is to find out the locant for the substituent, okay? Here, you have 6-membered ring, you have methyl group and methyl group, This is non-cyclic part, but you have only one carbon in the non-cyclic part. You have 6 carbon in the cyclic part. Therefore, the parent will be the cyclic form rather than linear form like this. In this case, parent is cycle and methyl group is the substituent. So if you look at the parent, that's the cyclohexane. Now in the second step, you have to put a number on the the substituents. We can think of 2 ways. You can start, try to minimize the number for the substituent. So you have to start either from here or the other carbon here. So make the position for the substituent the minimum, right? Now you have to decide whether you are going to turn around, clockwise, or whether you are going to turn anti-clockwise. This is a clockwise way to put the numbers on the cycles. This is anti-clockwise to put the number of the cycle. If you use this numbering system, you can put 1 and 3 for 2 methyl substituents. But if you use this numbering system, you will have 1 and 5 for 2 methyl substituents. Therefore, the left one is the recommended one. So the name will be 1,3-dimethyl cyclohexane instead of 1,5 dimethyl cyclohexane. Actually, the 5 is higher than 3, so this one is not recommended. Let's take on the second example here. We immediately know that the cycle form is the parent, right? Because it has 7 carbons, 1 carbon, 1 carbon, 2 carbons. Now you have 2 methyl substituents and 1 ethyl substituents. You can start from here, or you can start from here like this. If you start from here, everybody knows that we have to go anti-clockwise to make the number minimum. If you start from here, we should go the other way like this. If we use this locant system, the name will be, this is ethyl, this is dimethyl, and ethyl comes before methyl. Therefore, the nomenclature for this compound will be 2-ethyl, 1,4-dimethyl cycloheptane. In this case, 3-ethyl, 1,4-dimethyl cycloheptane. If you compare this two nomenclature, 2 is lower than 3. Therefore, nomenclature on the left side is recommended. Okay. Let's try to compare 2 molecules in this slide. The left one, you have 2 methyl groups on the upper side. You have 2 methyl groups on the other side, all right? One is up, the other one is down. In this case, both of them is up. If you try to overlap them, you will immediately find out there is no way to overlap it. If you cannot overlap, that means they are different molecules. So in this case, these 2 molecules are different, but the molecular formula is the same, so they should be an isomer. If you compare these 2 methyl groups are on the same side, so we call this is cis isomer. If 2 methyl groups are opposite side, then we call trans isomers. Parent is cyclopropane. You have 2 methyl groups. So this compound will have a name 1,2-dimethyl cyclopropane. This compound also will have 1,2-dimethyl cyclopropane. However, they are different compounds, so we have to distinguish them. we call this as a cis 1,2-dimethyl-cyclopropane. We call this as a trans 1,2-dimethyl-cyclopropane. Now, this kind of cis-trans isomer we call stereoisomerism. So far we discussed about the constitutional isomers, like here, this is butane, this is normal butane, this is isobutane. They have different connections between atoms. So if you want to convert this compound, this isomer into the other isomer, you have to break bond and change the arrangement of atoms. Otherwise, there is no way to convert one isomer into the other isomer. And we call this as a constitutional isomer. In the other way, the stereoisomers are the isomers with the same connections but different three-dimensional geometry. Here, you have relative arrangement of this carbon of these three groups are the same here and here. This part is also relative arrangement of this carbon around this carbon is the same as this, but the three-dimensional structure is different, right? So in this case, we call stereoisomers. The same connection, you see here, if you compare these two carbons, the connection is the same, right? But the three-dimensional geometry is different. This is the diagram for the classification of isomers. We classify isomers in two classes. Constitutional isomers that we just learned in the previous chapters, and stereoisomers. Stereoisomers include several other kind of isomers, like can be divided into enantiomers and diastereomers. We learn about enantiomers in chapter 6 or 7, 5, 6, 7, okay? Now we just learned the cis-trans isomers, and cis-trans isomers belongs to diastereomers, okay? And diastereomers contains other kind of the stereoisomers called configurational isomers, configurational diastereomers. So diastereomers can be divided into configurational isomer and cis-trans isomers. And all other, all stereoisomers except enantiomers, actually the enantiomers are in a mirror image relationship, are called diastereomers. And if they are cis-trans isomers, then we call cis-trans. If they are not cis-trans isomers, then we call configurational isomers in diastereomers. We'll look at this diagram quite frequently. So we'll talk about the stability of alkanes. Also, we'll introduce the concept of strain energy. If you have cyclic compounds and you react with oxygen, that is the oxidation with the oxygen molecule, and this is just like a burning. You burn the cyclic compound with the oxygen molecules. Burning itself is a chemical reaction, right? So it produces CO2 and H2O. In this reaction is generally exothermic reaction and generate heat. The amount of heat depends on what kind of cyclic compounds you have. This heat can be represented as the heat per molecules, right? If you use cyclopropane, you generate about 110 kilojoule per mole. But if you have a cyclobutane, a little bit less. If you have cyclopentane, dramatically decrease. If you have cyclohexane, wow, almost no energy is generated. Now, if you have a 7-member ring, 5, 8, 9, then it increases a little bit and then decrease again. What happens? Generally, we are interested in small cyclic compounds. We are not interested in very large cyclic compounds because large cyclic compounds are seldomly found in the nature. But the small cyclic compounds plays very important in organic chemistry and biomolecules also. So we'll focus on 3-member ring, 4-member ring, 5-member ring, and 6-member rings, right? As the number of carbon increases, the amount of generated heat decreases, okay? And the heat generated here is a kind of energy, and that means the energy of cyclic compounds contains some kind of energy, right? That means the energy level of cyclic compound is relatively very high. So after burning with oxygen, they lose the cyclic structure and generate heat. Therefore, we can consider this heat is generated probably due to the presence of cycles. Because the cycle is a ring, and we suppose that the ring contains energies, and we say the energy included in the cyclic structure is due to strain, right? We call it a strain energy, right? If it is due to the ring structure, then we call it a ring strain, right? There are several other kind of strains. We already learned it, torsional strain and the Streck strain. So in this chapter, we introduced the concept of ring strain. So we learned the 3 different kinds of strains, actually strain energy. Ring strain energy, torsional strain energy, and Streck strain energy. We'll apply the concept of these 3 different kinds of strain energy into the cyclic compounds. First, angle strain is expansion or compression of bond angles away from the most stable. What does that mean? If you look at this carbon, the carbon is sp3, and we know the angle of the tetrahedral carbon in about 109. But if you look at this geometric structure of the cyclopropane, this should be about 60 degrees. So this angle is not perfect angle for sp3 carbons. Because this angle is not perfect, it's not good for the sp3 carbons. sp3 carbon is not stable. If you look at cyclobutane, it's 90 degrees, a little bit better, but still smaller than the 109. Pentane is 108. Wow, it is almost close to 109. For cyclohexane, it's 120. So in this case, the angle is larger than 109. Now, this angle strain is due to the expansion or compression of bond angles away from the most stable. Namely, for the sp3, it should be 109. So in this case, cyclopentane is very close to 109, so it probably is very stable. The torsional strain means we already learned that eclipsing of bonds on the neighboring atoms. For example, in this case, this CH and this CH are on the same direction. They two CH bonds are almost in the same plane. So this bond, this bond, that's the electron cloud, all right? You have two electrons in this bond, and it's negatively charged. You have two electrons in this bond, it's negatively charged. So if they're in the same plane, they will have repulsions. Because they have repulsions, they don't like each other, and it will cause to make this molecule in a higher energy level. Steric strain is a repulsive interactions between non-bonded atoms in close proximity. That means steric strain is due to the bulkiness of an atom or atomic groups, right? Let's take this example for other cases. And also, we use this concept for the analysis of conformation of cycloalkanes. Let's take a look at the cyclopropane. We know the angle is about 60 degrees in a geometry. It's much shorter than 109. Therefore, we can say, wow, cyclopropane compound will have very high angle strain energy. Secondly, this carbon requires sp3, but the cyclopropyl geometry does not allow 109 here. So, and that's the reason why they have an angle strain. But if you look at this structure, these two CH on the almost they are in the same plane, just like here. You have 1, 2, 3 carbons, 2 CH bonds on the same direction, and we can expect a torsional strain between CH in the front carbon with the CH electrons in the bond, in the CH bond in the back carbon. Okay, so because they are eclipsed, they will have a torsional strain. So cyclopropane will have angle strain and also torsional strain. Due to the angle strain, it should be 109. However, for the cyclopropane, it cannot make 109s, but this should be sp3 hybridized orbitals. So they are not like this. If it is 109, it will be in a linear line. However, two orbitals, they are bented. These two orbitals overlapped, not in a line, they are bented. So the bond between carbon and carbon in the cyclopropane is just like a bented bond like this, not perfectly linear, because of the requirement for 109 degree for sp3 hybrid orbitals of the carbon in the cyclopropane. Okay. For the cyclobutane, we can see angle strain, yes. We can see torsional strain, yes. In order to, all molecules try to maintain the low energy states. So, in order to make this angle larger than 90 and closer to 109, the cyclobutane undergoes the puckering like this. Okay, all these 4 carbons are not in the same plane; they are out of the plane. By this puckering, they can expand these angles larger than 90. So lower the angle strain energies like this. Okay, this is Newman projection of the puckered cyclobutane. Okay, for the cyclopentane, we can think about puckering of the cyclopentane also. Cyclopentane is 108 degree, but it's still there is a difference from 109, so they have little puckering also. We can see the Newman projection like this. If you look at these Newman projections, we immediately know that all these carbons are not in the same plane, right? They are puckered. So 4-membered ring and 3-membered ring are puckered. However, the 3-membered ring can never be puckered because the geometric restraint. We'll take a look at the conformation of a cyclohexane. Let's see take a look at the planar structure of the cyclohexane, and this angle should be 120. It's much larger, too large for, compared to 109. So in this case also, they'll have a puckering. And usually the six-membered ring will have a typical puckering, like you put this carbon up, you put this carbon down, or you put this carbon down, or the other. This is 1, 2, 3, 4, 1, 4 position, okay? The other carbon can goes up, then you will have like this. We can draw the Newman projection for this also. 1, 2, 1, 2, and 5, 4, 5, 4, and 5, 4 like this. We can immediately tell that all 6 carbons are not in the same plane because of the Newman projection like this. How do I draw the cyclohexane? In the cyclohexanes, you have to remember that this should be parallel here, right? This should be parallel. This should be parallel. Okay, we can pick up this two lines, two bonds should be parallel each other. So when you draw the six-membered ring, you draw like this, and this. When you draw this, these two pairs, try to remember 2 pairs should be parallel. Okay, this should be parallel this should be parallel this should be parallel this one should be parallel with this, right? And we call this as chair conformations. And in these chair conformations, we can also put this up, then you will have this, and we call this is a both conformation. But even in this both conformations, you have 1, 2, 3, 4, 5, 6 carbons, but you have 1, 2, 3, 4 carbons. These 4 carbons are not in the same plane. So this carbon, actually, if they are in the same plane, they should be here, but goes up, and so we call this is twisted. The reason it is twisted is because they want to avoid torsional strain between this CH and this CH, okay? So this is a twisted both conformation of the cyclohexane. If you compare the energy, this twisted both conformation of the cyclohexane with the chair conformation of cyclohexane, there is energy difference of 23. Oh, okay. So far, we learned about the conformation of a cyclohexane. Okay. Next time, we learn more about the energy of the cyclohexane form, because the cyclohexane plays one of the most important conformation in many biological molecules and in other organic molecules. Okay. See you next time.